When weather conditions are poor, most larger airports utilize the Instrument Landing System, or ILS, approach as their primary way of guiding aircraft to the runway safely. The technology behind the ILS is a proven one that is decades old and when linked to an autopilot can enable aircraft to auto-land in 0-0 weather conditions. The ILS is considered a precision approach, meaning it provides both lateral and vertical guidance to the runway within the precision standards as specified in ICAO Annex 10. The pilot will follow this guidance down to a decision altitude, or DA, at which point the pilot will determine if the runway and landing environment are in sight and if it's safe to continue to descend to land on the runway. If the pilot does not see the runway, a missed approach must be initiated. There are 3 categories of ILS approaches, 1, 2, and 3, with each one having different approach minimums. Category 1 approaches are primarily used in general aviation and allow the aircraft to descend to approximately 200 feet above touchdown zone elevation. Category 2 and 3 approaches allow the aircraft to descend to 100 feet above touchdown zone elevation or lower, with potentially no actual decision height or visibility required. However, those categories require special equipment on the aircraft and special aircrew training. The ILS can be divided functionally into 3 parts: guidance information, range information, and visual information. Guidance information comes from 2 highly directional transmitting systems. The Localizer provides horizontal guidance, while the Glideslope provides vertical guidance. Range information can be provided from marker beacons, DME, and/or precision radar. Finally, the visual information comes from the approach and runway lighting systems. ILS approach charts list the Localizer frequency in the header. The frequencies are limited to just 40 specific options between 108.1 and 111.95 MHz. When the Localizer frequency is entered, the Glideslope frequency will automatically get tuned within the nav receiver based on known frequency pairs. A listing of the published ILS frequency pairs can be found in AIM Table 1-1-4. Let's begin by taking a deeper look at how each of the components work, starting with the Localizer. The Localizer is located at the far end or departure end of the runway it services. It emits 2 signals, a 90 Hz frequency on the left side of the runway and a 150 Hz frequency on the right side. The ILS receiver in your aircraft receives these 2 frequencies, and based on the signal strengths of the 2 frequencies, it can determine which side of the Localizer you're on. If the 2 frequencies are received equally, then your receiver knows your location is along the extended centerline of the runway. Conversely, if one signal is stronger than the other, it means that you are off-center towards the side with the stronger signal. If your receiver detects the 90 Hz frequency more than a 150 Hz frequency, then it knows you are to the left of the centerline. The CDI will then deflect to the right, indicating that you need to correct to the right. Similar to VORs, the closer to the antenna the aircraft is, the tighter and more sensitive the course will be. Localizers are calibrated to have a course width of 700 feet when over the runway threshold, so the runway length will determine how wide the course is along the approach. The longer the runway, the narrower the course. Also similar to VORs, localizers have a service volume. A localizer's service volume is limited to within 18 nautical miles and 10 degrees of centerline, or within 10 nautical miles and 35 degrees of centerline. Outside of the service volume, you could receive erroneous indications or no signal at all. The Glideslope is essentially a localizer rotated to stand vertically. It is usually calibrated to provide a 3-degree glide path with a 1.4-degree vertical course width. It is typically found 750 to 1,250 feet from the approach end of the runway and is offset from the centerline 250 to 650 feet. Just like the Localizer, it emits 2 signals to provide vertical guidance to the runway, a 90 Hz above and a 150 Hz frequency below. Receiving both frequencies equally is considered to be on Glideslope. Glideslopes are normally usable up to a distance of 10 miles. The Glideslope antenna creates mirrored transmissions of the true Glideslope, which produce false signals above the actual Glideslope, with regions of no signal in between. That means with a standard Glideslope of 3 degrees, the transmitter will produce the real Glideslope at 3 degrees and 2 false Glideslopes at 9 and 15 degrees. Generally speaking, Glideslope intercepts beyond 10 nautical miles away may lead to you receiving a false Glideslope signal instead of the real one. Following a false Glideslope will result in an extremely high rate of descent needed to maintain it. Because of the potential of capturing a false glide slope, the correct procedure is always to capture the glide slope from below, and to verify the aircraft altitude matches the published glide slope intercept altitude on the approach chart. Due to the positioning of the glide slope antenna close to the approach end of the runway, the glide slope is subject to another issue known as distortion. The antenna location is a place where moving objects such as other planes, airport vehicles, or even animals can get in between the aircraft and the transmitter, causing the glide slope signal to be blocked and causing a sharp, drastic fluctuation on the CDI. If an erratic glide slope is encountered, the approach should be abandoned, as the signals being received are no longer reliable. To minimize these situations, airports have established ILS Critical Areas. These locations, which are identified with signs and pavement markings, serve as areas that aircraft and other ground vehicles have to stay clear of when instructed to do so by ATC. These areas are most likely to be active when the reported ceilings are less than 800 feet and/or the visibility is less than 2 statute miles. ILSs have been around long before GPS and distance measuring equipment were widely available. Because of this, marker beacons were commonly used for range information to determine distance from the runway threshold. Each marker beacon emits an elliptical signal that, when crossing over, is denoted visually and/or by a distinct tone in the cockpit. There are 3 types of marker beacons found along an approach. They are the outer marker, the middle marker, and the inner marker. The category of the approach being flown will determine which marker beacons are associated with the approach. Since GPS is now widely available, marker beacons aren't as common anymore. The outer marker is located between 4 and 7 miles from the runway threshold and identifies the location where glide slope intercept occurs, or for a localizer-only approach, the location of the final approach fix. It is denoted by a flashing blue light and a low-pitched Morse code tone of repeating dashes. The middle marker is located about 3,500 feet from the runway threshold and identifies the Category 1 decision height, approximately 200 feet above touchdown zone elevation. It is denoted by an amber light and a medium-pitched dot dash repeating tone. The inner marker is found on Category 2 and 3 approaches. It is located between 1,500 and 2,000 feet from the runway threshold and identifies Category 2 and 3 decision heights, which are approximately 100 feet above touchdown zone elevation. It is denoted by a quick flashing white light and a high-pitched repeating dot. On some approaches, there'll be a compass locator co-located with either the outer marker or middle marker beacons. These are low-powered NDBs that have a range of at least 15 nautical miles. Compass locators co-located in outer marker are called locator outer markers. These transmit the first 2 letters of the localizer identification group. Locator middle markers are compass locators that are co-located with middle markers. These transmit the last 2 letters of the localizer identification group. While NDBs are few and far between, they still may be labeled on approach charts since GPS can be used to identify their position. Aside from marker beacons, distance information can be obtained from DME, GPS, or ATC. The controller may be able to provide distance information if flying at an ATC facility equipped with precision radar. All Category 2 and 3 and most Category 1 approach runways have an approach lighting system associated with it. There are many types of approach light systems, with each having its own features and light intensities. The approach lighting system is designed to aid the pilot in transitioning from the instrument flying environment to the visual flying environment to identify the runway. It is vitally important to brief and know what lighting system is installed to be sure that the proper runway is in sight. Flying an ILS starts with tuning and identifying the localizer frequency. For this example, we'll tune and identify 110.3, the ILS 8 into San Juan International Airport in Puerto Rico. The approach begins with first aligning yourself with the runway using the localizer. This is usually done through ATC vectors or with a procedure turn. Let's say you're approaching the airport over the initial approach fix of Dorado and flying towards the intermediate fix of Wesson, where you'll intercept the localizer no lower than 3,200 feet. Assuming you've been giving your approach clearance, follow the descent profile once you've passed Wesson. This involves you descending from 3,200 feet down to 2,400 feet at Joral, and then down to 1,600 feet, maintaining 1,600 feet until the glide slope begins to center. From there, all you need to do is keep the green localizer CDI and glide slope diamond centered. This should remind you of flying an LPV approach. Remember, both the localizer and glideslope increase in sensitivity as you approach the runway, so focus on making small corrections. Apply corrections between 1/2 and 1 degree of pitch towards the diamond, and 5 to 10 degrees of heading towards the CDI needle. Applying too much correction is called chasing the needle, and will lead to erratic descent. 311 feet is the decision altitude for this approach, so at that point, if the runway or approach light system is not in sight, you must perform a missed approach. If you meet the requirements to land as specified in 91-175, keep using the localizer and glideslope to continue to the runway. This approach was designed for low visibility, so ensure that you continue to track the navigational aids all the way to the roundout. Another example is the Localizer 4 right approach into Honolulu International Airport in Hawaii. The Localizer approach is different from an ILS because it does not have a glide slope and therefore does not provide vertical guidance. This approach also has a note that says DME required. Our aircraft do not possess DME receivers, and the bearing pointer won't display distance information from the localizer antenna. Therefore, you can substitute GPS for DME and overlay the approach by loading the approach in the GPS in order to identify all the fixes on the approach. You will either be radar vectored to the final approach course, or you'll need to complete a procedure turn. In this instance, let's say you received a clearance to fly the approach starting from the initial approach fix of Pearly, where you'll then proceed outbound on the localizer. You must fly your outbound leg in your procedure turn to remain within 15 nautical miles of Pearly. Over Pearly, descend to be at 1900 feet by the completion of the procedure turn. The common 45-180 procedure turn type is accomplished by turning 45 degrees to the left to a heading of 177 degrees for the outbound leg, then a 180 degree turn to the right to a heading of 357 degrees to intercept the localizer. With the localizer intercepted, descend to 1,500 feet again until you reach Pearly. From there, you must calculate your rate of descent to arrive at the missed approach point at the MDA of 460 feet. When there, if you do not have the runway environment in sight, remain at 460 feet until you've reached the missed approach point, Phalos. If you do have the runway in sight, you may continue your descent to a landing. Up until this point, we've been discussing the utilization of the ILS components for the primary runway it was intended for. This is called the front course. However, some installations allow for the use of the localizer from the opposite direction, called the back course. Localizers transmit both front and back course signals from their antennas. The front course is what is used when flying standard localizer and ILS approaches, with the antenna located at the departure end of the runway. The back course refers to the signals emitting from the back side of the antenna, which means it's located on the approach end of the runway you're landing on. You'll find localizer back course approaches on runways that already have ILS or localizer approaches installed, but pointed in the opposite direction. The localizer back course approach allows for approaches in both directions with only one system installed. This is beneficial when one runway is active more often than the other. For example, on the east coast of Florida, the wind is predominantly always blowing from the east, so most runways will be situated east to west, with the easterly runway being active most of the time. So an ILS installed for the east runway is used to create a localizer back course approach for the west runway. Keep in mind, however, that just because a back course signal exists does not mean you should use it. The AIM states that you should not use the back course for an approach unless a back course approach is published for that runway. For pilots flying back course approaches using a CDI that is independent from their heading instrument, you must be aware of reverse sensing when flying towards the airport. This occurs because the course deviation indicator is not aware of your aircraft's heading or position relative to the fix. Remember that localizers emit two signals, a 90 Hz signal to the left and a 150 Hz signal to the right when on the front course. On the back course, it will be reversed, and the 90 will be on your right and the 150 will be on your left. So no matter what you have the OBS set to, you will get reverse sensing because this heading set in the CDI does not matter. If you drift to the right and the receiver is picking up a stronger 90 Hz signal, the CDI will move to the right, which on the front course is correct, but on the back course will be the opposite. So when flying inbound on the localizer back course, it is necessary to fly away from the needle in order to correct for any deviations. This procedure should also be followed when flying on the front course of the localizer, but in the opposite direction away from the airport. Remember, it does not matter what heading is in the CDI when tuning in a localizer back course or front course. with the OBS knob. Because of this, there is no way to eliminate reverse sensing without using an HSI. It is good practice to turn the OBS to the final approach course to remember which heading should be flown on the approach. Flying back course approaches with an airplane equipped with an HSI makes it possible to remove reverse sensing from the CDI. An HSI combines a heading indicator with a CDI. When flying a back course approach, the OBS needle is sent to point to the front course of the localizer. The CDI needle will still deflect as it would for a back course. However, because the CDI is essentially turned upside down, it looks correct to the pilot. When configured correctly, the pilot will have normal sensing and will fly the needle like a regular localizer approach. Once the CDI or HSI is set, flying a back course approach is just like a regular localizer approach. Track the needle inbound, making corrections as necessary, and reference step-down fixes to ensure proper descent down to the MDA. On a back course approach, the missed approach point may be farther away from the runway and the minimums may be higher. Remember that the antenna is located just prior to the runway threshold, which makes the needle very sensitive as you get closer to the runway. Be aware that as you continue to track the back course, you will lose signal as you cross over the antenna, much like a VOR. An ILS approach is a precision approach that provides both vertical and lateral guidance to the runway. With typical minimum and visibility requirements that allow a landing with 200-foot ceilings and a half-mile visibility, the ILS approach will remain a favorite approach of pilots in poor weather conditions.